Hello, welcome. Who knew so many people wanted to learn about stateful storage? So my name's Alex Chircop. I'm a chief architect at Akamai's Cloud, and I'm also a member of the technical oversight committee for the CNCF. This is my colleague.
Hey y'all, my name is Lori. I'm the head of community at Percona, and I'm also a CNCF ambassador.
Hey, I'm Alex Reid. I'm a principal engineer at Akamai.
And last but not least, my name is Chris Milsted. I'm a product architect at Akamai as well. Welcome everyone, and back to you, Alex.
Okay then. So why should we be thinking about cloud native storage? Because it's often something that's ignored in our environments. I mean, seriously, hasn't everything been stateless forever? Now, this is something which I always put up in all my talks, to kind of say there is no such thing as a stateless architecture. It's just someone else's problem, and it's probably all of your problems, or some of your problems, because all applications end up storing state somewhere. And why would we want, therefore, our storage to be cloud native? Because, of course, we've learned so much over the years from our Kubernetes environments, where we've made workloads declarative, and self-healing and auto-scaling. So, of course, all of the stateful workloads can also benefit from the automation that you get from a cloud-native environment. The ability to easily scale and deploy complex topologies, the self-healing and the automatic failover, and of course the performance. And what do we mean by all of those things? So when we talk about automation, we're talking about the declarative nature of cloud-native storage. You can have a set of YAML that defines not only that you want to run or define a stateful workload, but it also allows you to define very complex topologies using operators, and we're going to give some demos to show that. It also allows you to easily scale and apply scaling as your capacity or your RPS requirements grow over time. And it provides an automatic self-healing. So when you want to upgrade nodes, when a node fails and you need to fail over a workload somewhere else, you get that automatic self-healing failover. And when it comes to performance, with all the flexibility that we have with nodes in a cloud-native workload like Kubernetes, where you have local NVMe, for example, or distributed storage solutions that you can utilize, you're also talking about now getting native performance. Like, there isn't an overhead of deploying in a cloud-native environment, and more importantly, the ability to get deterministic performance, right? So the ability for a particular query to always take the same amount of time every time. And when we talk about cloud-native storage, it's obviously more than just storage. You know, we're very familiar with, you know, the block volumes or the file systems and the shared file systems, which are much more common nowadays with machine learning workloads. But it's also, of course, the object stores and the databases and the key value pairs that you're connecting to and actually querying. And today we're going to talk about a demo of a complex database topology and a very fast scale-out key value demo too. But it's not just those products. It's all the ecosystem that goes around this. So all of the Kubernetes integrations that make this possible, like the CSI drivers for block storage, the cozy drivers for object storage, and all of the operators that make this possible. And the operators, of course, also enable all of our day two operations. So things like upgrades and the ability to back up, the ability to fail over and perform disaster recovery. And then it's taking advantage of the rest of your cloud-native stack, because you've already invested in the observability and the secrets management and certificate management and the encryption and the scaling and elasticity, right? So when you want to be able to move to more cores, or when you want to be able to upgrade the number of nodes for a distributed system, the cloud-native environment makes all of these things so much simpler. Putting my CNCF storage tag hat on for a little bit. The tag has put together a storage white paper, which kind of covers some of the landscape of the cloud-native storage environment, covering things like what the attributes of a cloud-native storage system look like. So, you know, when we're thinking about high availability, Also thinking about what the consistency requirements are, for example, or what the durability requirements are. And when we're talking about scale, what are we talking about? Is it just, you know, the number of requests or the number of IOs, or is it the number of throughput, etc.? And different systems provide different benefits. So it's really important that you work out what your application needs. And of course, in cloud-native systems, there are multiple layers of virtualization. You have object stores built on file systems, or file systems built on object stores, or block devices built on all sorts of complicated systems. So in the end of the day, you do need to understand those layers, where the caching in those layers happen, and that enables, you know, the performance and the scalability. And of course, we also talk a lot about, you know, the deployment options, the topologies, the management interfaces like CSI, for example, and those different access interfaces too. Now, putting my TOC hat on for a second, it's also important to say that, you know, we're doing some demos today for a couple of different projects, but there are lots of CNCF storage projects, both graduated and incubating. So things like Rook, which provides an operator for Ceph, Vitess, which is a distributed MySQL cluster, etcd, which of course you will run in your Kubernetes environments, TiKV, which we're going to be talking about today, CubeFS, which is recently graduated, just a couple of months ago, shared file system used for a lot for AI and machine learning. And there are some very cool incubating projects too. But there are 200 and something projects in the CNCF now, so it's really a good idea to navigate those and have a look at some of the sandbox projects where a lot of the innovation and experimentation is happening too. So now we're going to do a little sacrifice of the demo gods, and I'm going to pass it over to Chris.
Hello, everyone. Nice to meet you all. I'm going to talk about CloudNativePG and a demo with that. All of the kind of repo, all the kind of YAML, all you need, and the Terraform and everything you need to get this up and running is in there. We will upload the slides after the talk because we found spelling mistakes this morning that we fixed, so we haven't done that yet. So I'm going to go back about 20 years when I first started in IT. Stateful applications were Oracle clusters. I think I remember Oracle 7 was the first production cluster I broke. And we basically got given, I went and had a look today, this is Oracle, the latest version of Oracle Grid Infrastructure. It's a 290-page PDF if you want to install it, and that includes every option and every configuration you need to run that database. Generally, that's not how you'd set things up, and I remember after that we had, I think Sun had the blue books, IBM had the red books. So we got people using these things in production, and then we worked out actually the hardware's different, how they install it's different, what the workload's different. So we'll now come up with another book to tell you how to use the application. All this changes in Kubernetes. The thing about Kubernetes is it basically takes an underlying platform and abstracts all that complexity. So this is my argument to you today, is running stateful workloads on top of Kubernetes is the best, most repeatable, and I would argue, in some respects, the safest place to do it now, when you start looking at things like pod disruption budgets and all of the other inbuilt mechanisms in Kubernetes to make them safe. All this builds on the operator framework. So, you know, that 290-page document that it took a bunch of engineers to write. The Red Book, it took a bunch of field engineers to go and write and distill all that information about as well. All of that information can be captured in these operators. These are programmatic applications that will basically make your application work in the way it's designed to. So you can distill that 290-page document into 90 lines of YAML. The indentation is completely broken when I pasted these into the slide, so please don't copy them from here. Go look at the GitHub repository. But the important thing here, instances 3, give me a highly available clustered master and 2 replicas of my Postgres install. initdb on the left-hand side, initialize my database from scratch. Plugins, I'm using Barman here to stream my well logs out to an object store in another location so that I can recover this database. And on the right-hand side, instances 3, and I'm doing an external cluster restore. So these 90 lines of YAML will give you a highly available stateful application and recover it from a remote object storage. Much easier than going through all those books. Quick picture. If you want to come and talk to me more about this, you can find me at the Akamai stand. Akamai and Linode are the same thing, and I'm building all of this on top of the Linode Kubernetes engine. So if you want to talk about managed Kubernetes, come and have a chat to me there about that as well. And just to prove there's no smoke and mirrors, and I can show you this at the stand, with the system ID from the backup and the restore on either side are the same. So let's see it in action. Let's see what happens when we fire up those 90 lines of YAML. And I'm just going to have to change this to high definition because the Wi-Fi has gone for a burn. So what we're doing here is we're going in a live demo, and we're actually going into the Cloud Manager, and we're killing one of the nodes where our live database is running. Now, the operator is fantastic. They've actually made a conscious decision in Cloud Native Postgres to write their own operator, and that's because your storage could be local and your storage could be remote. So we've gone in and killed our node there. If we fast forward a little bit into the demo, you can see we've got some red lines. Red lines are bad. We've lost one of our instances. So as we go through the demo and have a little bit further in time, a little bit up here, what we'll start to see is Kubernetes is starting to recover. So Kubernetes has gone, hey, wait a minute, one of my nodes is missing. So Kubernetes goes, all right, I'll bring your node back and I'll get my node into the ready state. At this point, the Cloud Native Postgres operator comes along and goes, how was your data laid out? Was it replicated? Was it using local storage? Was it using remote storage? Do I need to recreate volumes? Do I need to recopy data into those volumes? Do I need to just bring up a new node and attach my storage that's on a remote network attack storage back to the Kubernetes node that's now recovered and is now up and running? So as we go through this, you'll see nodes are starting to come up. Pods are starting to initialize. You can see them going to the init state here. And it's starting to say, actually, reinitialize those pods, reattach the storage to those pods, and bring that database back up into a running and working state. So as we get to the end of the demo here, you'll start to see that the container comes into a, I think it comes into, next one. And here we go, standby starting up. So on the bottom there, you can see the status has gone to starting up. So what we've done is basically killed one of our stateful applications. Don't have to worry about how it's laid out. Don't have to worry about anything. The operator's just taking care of all of that. And all the while, all of our WAL logs, all of our backups are being streamed remotely. So as we come out of this quick demo we've seen there of how we can recover from the nodes. How do I get out full screen? Let's press escape. There we go. We come out of presentation mode. Brilliant. So just to kind of summarize that last bit there, what was good about that, and what did we see from everything that was working on that? The pod disruption budgets. You can go into a Kubernetes cluster and you can try and kill pods, you can try and kill nodes, you can try and take things down. If your application is set up with pod disruption budgets, you have a safer, more stable, more resilient, persistent workload than if you're running on just on commodity infrastructure. And all of these other components added by the operators give you all this additional componentry out of the box. You don't have to go and read a 290-page manual to understand what you're talking about. So with that, I'm going to hand over to Alex, who's now going to show you another demo and another part of stateful applications running Kubernetes. Over to you, Alex.
Cheers, Chris. Right, so we're going to take a look at TiKV. So TiKV is a highly scalable, low latency distributed key value store. So it provides both a raw key value API and also an ACID compliant transactional API. So you can think of your raw key value API as get, put, delete for a key or batch of keys, and then ACID compliant transactions obviously allow you to compose operations together and submit them to the database as one atomic operation. And you can build on top of that to do more complex databases like SQL, for example. So TiKV actually has an SQL component which is built on top of the low-level TiKV database. So it's very easy to deploy in Kubernetes, and it's a graduated CNCF project. So it's mature, it's been used in production by a bunch of companies. So let's just touch on some of the kind of highlights of TiKV. So it's really designed with scale in mind. It can scale horizontally to hundreds, if not thousands of terabytes of data, billions of keys, and hundreds of thousands of RPS. In fact, millions of RPS, and hopefully that's what we're going to see today. So it does that by splitting your key space up into regions. Typically, a region is about 100 megabytes, but that's tunable. And it'll split those regions up among your storage nodes. So as your capacity or RPS requirements grow, you can add more nodes to your cluster, and TiKV has got a bunch of intelligence to scale out that data, balance it, address any hotspots, things like that. And obviously all the fault-tolerant kind of stuff we come to expect as well from a production key value store. So it's also very low latency. It's definitely capable of operating in that kind of 1 to 10 millisecond latency range. That's for reads and writes. And that's largely in part because it's based on RocksDB, which is a lightning-fast, non-distributed key value store, which has had over 15 years of kind of engineering and optimization time behind it. And of course, it's kind of cloud native. It's got a fantastic Kubernetes operator to handle your deployment upgrades, automated failover, and it comes with a bunch of great observability out the box. So in particular, the kind of pre-configured Grafana dashboards are really useful, and we'll dig into that in a sec. So installation-wise, there's not a whole bunch to say here. It's your standard Kubernetes install process. There's a bunch of CRDs you can install. Then you grab the operator. Helm's probably the easiest way to do it. And then after that, you can define your cluster and apply it. So before we go into the demo, I'm going to just show you an example cluster definition I have here. And this is the cluster definition we're going to use in the forthcoming demo. So we've got 5 copies of the data. We're not cheating here. This is a production level replication. We want to be fault tolerant. We want to be able to lose 1, if not 2, if not 3 nodes. We have 12, that second line down, there are 12 replicas. That means we have 12 nodes for storage. So in this demo, I'm going to load up 10 billion keys into the database. Well, I'm not going to do that as part of the demo. I did that beforehand because it takes a while. So we've got 10 billion keys, 5-way replication. That's 50 billion keys in total, about 1.5 terabytes of key value data. Next line down is really important. So you can see here we've set the storage class to SSD storage. So what we've done here is we've exposed the local NVMEs on the Kubernetes nodes through to the TiKV pods. So again, like Chris's demo, this is running in LKE, Linux Kubernetes engine. And one of the benefits of LKE is you get access to these fast local NVMEs. So if you want to be doing low latency, hundreds of thousands of IOPS on your key value store, you better have some pretty quick storage. And the final line there is just showing that we've used the Kubernetes pod anti-affinity feature to ensure that we have 1 TiKV pod running per Kubernetes node. If you have beefier nodes, you might want to consider running multiple pods per node, but TiKV, in the way we're using it, it's quite a hungry application, so we want to ensure that that pod gets full access to the node. Okay, let's start the demo. Okay, so this is my 20-node Kubernetes cluster. 13 of the nodes I've reserved for TiKV. Sorry, 13 of the nodes I've reserved for TiKV. The other 7 are for the benchmark client. So the benchmark client here is a tool called GoYCSB, which is an open source database benchmarking tool. And we've just put some scripting around it to kind of run it in Kubernetes and bring up multiple pods and do things like collate the results afterwards and analyze latencies, which we won't get into today. So out of the 13 TiKV nodes, 12 of them are actually for storage, like I said earlier. One of the nodes and one of the pods is reserved for the Kubernetes, the TiKV control plane. So what I'm going to do is I've got a bunch of bash scripts that basically bring up my benchmark, and that's going to start running in a second. And the idea is we're going to try and target 1 million random read IOPS. So those 7 benchmark nodes, we're going to spin up about 15 benchmark pods, I think, across those 7 nodes, and they're each just going to read a random key out of that 10 billion key space. And the idea is, can we hit 1 million IOPS on a fairly modest cluster? So there we go. That's the benchmark just coming up now. We'll give it a bit of time to run, and we're going to jump over to the Grafana dashboards and see what's going on. So like I said, TiKV comes with a bunch of super useful dashboards. You can get a high-level view of your cluster, or you can really get into the weeds and look at specific components within the stack. This is just one of the dashboards. There's probably about a dozen others. But you can see even this one has got a whole wealth of information. And what we're going to do is we're going to jump into one of the more high-level panels, the cluster dashboard. And as you can see, you've got, along the top row, you've got your available capacity, how much space you're currently using, all those kind of headline stats. Next row down, we've got things like CPU usage, in memory, and the row below that, we've got current queries per second rate, throughput, and there's a whole bunch more I can show you on that as well. So if we dive into the CPU panel, you can see we've got 12 TiKV nodes, our 12 storage nodes, and they're all running pretty hot, so between 900% and 1,000% CPU usage. As you'd expect, TiKV's balanced our data pretty evenly, which is why all the CPU usage across the nodes is pretty uniform. Just looking at the memory panel here, so we're using about 20 gig of memory on each of those TiKV pods. That's not a memory leak, it's nothing to be alarmed about. By default, TiKV will try and use a bunch of memory as an in-memory cache for your data. So depending on your workload, that can really accelerate performance. Probably not so much for this random read test because our working set is much larger than the available RAM in the cluster, but it's something to be aware of. And of course, you can tune all this. So just to prove it's not all smoke and mirrors, we're going to go into the gRPC panel and take a look at the queries per second dashboard. And it might be a bit small to see there, but I promise you I'm not lying. We've been pinned at about 1 million RPS for the past couple of minutes. Thanks. I'm going to hand it over to Laurie.
All right. Okay. So you got the theory and the education from Alex. You got the demos from Alex and Chris. And now I'm going to give you some real-world application of what we just heard about. So we are going to talk about Nokia and Civo. And just so you know, I have speaker notes on my phone. I'm not like texting people while I'm up here. Okay. So I work for Percona, and Percona is a 100% open source company, and being head of community for a 100% open source company has got to be like the highlight of my career. Why? Because everything that I'm talking about, everything that we do, everything that we build is open source. You can try it today, right? You don't have to pay us anything, but we're here to help you along the way. But again, 100% open source, so to be able to be up here on stage with Akamai and to talk about CNCF and open source projects, it's just awesome. So let's get into it. Nokia. You guys remember the phones? Yeah, okay. So Nokia is one of our customers, and we are going to help them. So they have 90,000 internal users, right? They have 6,000 projects, 5 data centers, and 61 petabytes of storage. So they're not busy at all, right? Like that's why no calls get dropped. So what is their main pain? Their main pain is operational efficiency, right? The lack of database self-storage, growing number of microservices, and what are their requirements? Number one, it's 100% open source, so they called us. Number two, they needed MySQL and Postgres support, which is cool. So what is the solution? So they decided to run databases on NKS K8, their version. They used our MySQL and Postgres operators to build a private DBAS. This allowed them to shift databases from virtual environments to Kubernetes to improve resource utilization and reduce infrastructure costs. Things cost money. And they shift the responsibility for database management left to the devs team. So they were responsible for their own path forward. And so like, just to do a little bit of a callback to what Alex was saying, this is a real life user taking advantage of automation, scaling, and day 2 complexity using Kubernetes. And it's Nokia, guys. Big telecom operator, Fortune 500 company. Ooh, hey girl, what you doing? All right, sorry. Civo. So Civo is a cloud-native service provider providing public, private cloud, all on Kubernetes. And you're like, okay, well, if you're already on Kubernetes, why do you need any help? Well, they wanted to launch a MySQL and Postgres DBAS on K8s for their customers. So what did they need? They needed something that was reliable. It was battle-proven database operators. They didn't want to create their own. They wanted something that they could just use out of the box. They needed isolated tenant and multi-tenant environment support. Again, open source and integrated with the Civo Cloud Control Plane. So open source, battle tested, an operator that works that they can count on because now they're going to have their customers count on it as well. My goodness. There we go. So what was the solution? They used our operators for MySQL and Postgres to automate operations in the backend. They namespace operator deployments to provide the required separation of tenants, which allowed them to create this great service offering for their customers, so they could launch a MySQL and Postgres, so their customers could launch MySQL and Postgres DBaaS quickly, so they could have their own control because it's a DBaaS. They could keep cloud native design approach, which is end to end, and they could continue to develop, continue the development of projects. But that's why they wanted open source, right? So they can continue to build on what they've already had going. So again, Alex gave you like the why. The guys gave you the how, and this is us telling you like it's being done every day. So hand it back to you.
So hopefully this was a bit of a whirlwind tour into why cloud native storage is a good idea, how you can deploy it in your environments today, and cover both some of the complex topology aspects as well as the performance, as well as some real-life use cases. And I think we have a few minutes left, so if anybody has any questions, we're open to taking any questions. There's a microphone right here to help yourself be heard. Don't be shy.
Is there any, God, that was a little bit loud. Is there any push from all of these operators to solve some of the underlying problems that stateful sets have, being completely immutable?
There is. So both in terms of helping with stateful sets, but also the operators in some cases move to doing deployments instead of stateful sets, and having the operators implement some of that logic and sort of correlating the workloads to the storage.
Yeah, thanks for the talks and demos. Could you talk a bit more about local storage versus network storage for Kubernetes services?
Yeah, so there isn't a one size fits all. I think when we talk about some workloads where you have like an individual workload that needs to move around a lot, then block storage, a distributed block storage capability or a shared block storage capability might be the right option. But more and more what we're seeing is the ability to utilize fast NVMe local storage, which is often not just extremely fast, but also much cheaper than attached block storage. And then using the facilities like what we just saw, say, with TiKV or Postgres replication to actually handle the availability and the durability side of things.
Can I just say one more thing on that, which is if you're trying to build something ultra fast like that and you don't control the network, the jitter and the latency, if you try and use network attached storage, will probably kill you. So I'd just say, I think as we get to more and more data workloads and all the kind of AI stuff we're hearing about, I think we're going back to local attached storage in Kubernetes clusters is my prediction. We'll see where we get to.
Quick question about scaling. How do we manage scaling the storage? So it's not entirely true with local storage because the scaling is finite due to the local storage, but in the case of attached storage, and also how do we scale the CPU of the database with a minimum of interruption in both cases?
So that is a how long is a piece of string kind of question, because it does very much depend on the actual database technology or storage technology that's in the stack. For things like, say, a relational database like Postgres, you often scale that by having sort of some level of vertical scaling, but then also having replicas that can be used to facilitate queries or data warehousing or that sort of thing. In modern systems like TiKV, where we have a very distributed sharded store, effectively you get more or less linear performance as you add the number of nodes and the number of local disks, and the operator and the control plane take the sort of add the cleverness, if you wish, to make sure that hotspots are identified and moved around and distributed across the cluster so that you can use all of the resources across all of the different nodes.
I'd almost say as well, it's as the database owner or operator, it's almost our responsibility to give the infrastructure or the cloud teams the input of what we need. But if you want to change the underlying nodes and move them to bigger, smaller nodes, or do a redirected restore to bigger nodes, a lot of these operators will just do that all for you nowadays. So actually, on the application side, it's nice and easy, but it is still our job to give accurate kind of inputs to the team of what we need underlying. And I think we're about to run completely out of time.
We are out of time. We're all going to be around, so if you have any other questions.